So I am the CEO of Clear Creek Solutions, CCS. We've been working with Heck Korea for almost 10 years on software development of the KLIDM. We also have other features that we develop in America for other people. And my son joined me a few years ago. He's an engineer and he helps with all of our training and application as well. So what we did, one of the things go ahead and move on to the next.
So we just went over with Clear Creek Solutions. We provide a complete range of hydrologic and stormwater modeling, which is especially intensive in the United States and in Western Washington, where we're based. And there's plenty of experience between all the founding members, and we chiefly created the wwhm 2012, which is what KLIDM is based off of, for Washington State Department of Ecology, which is in charge of all the jurisdictional requirements. And we've created a number of other similar software packages in the United States, chiefly in California. And so we teach wwhm, swmm, KLIDM, and HSPF and how these applications can be used to better our designs for the future. So now we're going to go over what exactly LID is and what we do to optimize it.
So what happens in between storm events, single events, what happens in between is actually more important than what happens during the event. Soil moisture, how long has it been raining, how much rain have you had recently, all this adds up. And so when we model the LID, we need to make sure that we take all of that into account. And that's continuous simulation, which is HSPF, which Mark mentioned. Using that model, when we actually look at what happens during an event, it's much more accurate and you get a better idea of what's happening. We use actual precipitation, long-term, sometimes 70 or 80 years, and we apply that in the model, and then we let the model tell us how the facility performs. So one of the main features of our models is the bioretention unit. It goes by many names: rain garden, or a bioswale, or bioinfiltration, or filtration, or stormwater plant. All of these that we've listed here essentially describe the same sort of thing. And we were contacted actually originally by Dr. Sin from Busan to work with him and help develop use of our bioretention module here in Korea, because it's unique. So basically, bioretention works by keeping more of the water on site, more evaporation, and more infiltration into the ground in a natural way. And so if done right, it is a great way of mitigating development and helping to keep the natural system in place. And that's what we're describing here.
So bioretention can really provide great water quality and hydro modification benefits if we actually design them correctly. And so that's the big if, right? So we use software such as wwhm 2012 or swmm, which combines the HSPF capabilities that Park touched on a little bit, and EPA SWMM. We're able to combine that into one software package and model the entire hydrologic cycle. And then we can use something like a bioretention, which is a low impact design, to keep more of that stormwater on site and utilize the historic rainfall data. So this is what bioretention modeling looks like in a model such as swmm. And I've been in Korea here for the last week, and in the winter it rains a lot. There is a lot of water. Reminds me of my home state, Washington State. So we have to model the entire hydrologic cycle. We just can't model one stormwater event. So that's why we're utilizing 50 or 60 years of stormwater data in something like swmm. So in the pre-developed scenario, this is before our project, we put in our project area. So we have, for an example, 2 acres of till forest. That's a very common forest type in Western Washington, to help generate the runoff for that entire model run, utilizing all of that stormwater data that we have. Then we input what our post-developed project is going to look like with added impervious area, roofs, whatever we're going to do. And then we now use the bioretention element. It can be used in a number of ways. It can be used for stormwater mitigation. It can also be used for filtration if we have pollution sources on our site. So we're able to model that here, and we can either size it for water quality or water quantity, and model the different soil layers inside of the software. And the best part is, you don't have to figure it out. We can actually auto-size this and auto-create, using our algorithms, a facility that is the most optimal for you. So it can take up the least amount of space on your project site and function how it's supposed to. So you could do that right here in WwH-swmm. This is a basic modeling process that I'm outlining here. And so we get a final model showing us the length, the width, what our freeboard is going to look like in our facility, the depth, and the kinds of soil layers that we're actually using. And then in WwH-swmm, you can go and analyze the hydrographs and take a look at all the information regarding that facility's performance right here in the software. And so, yes, we can do this in the software, and we're going to explain how the software does this, but most importantly, is this going to match up to the real world? It doesn't matter what you can design in software. If it never matches up to what's going on in real life, it doesn't actually matter. So he's going to explain how this actually works and how in-depth this process is.
So we set out to design the most physically accurate bioretention unit that we could, using a number of different equations. The essential design is this. We have soil here, and then we have outlet structure, vegetation, and everything on the surface. Go ahead and jump to the next one. So there are a number of equations that we use to move the water through the soil. And the main three are Darcy's equation, Van Genoegden equations, and the Greenamp equation, modified Greenamp. They work together to show how the water moves through the bioretention unit one step at a time. So we deal with these different factors, the head, the bubbling pressure, the soil moisture, the saturated conductivity, hydraulic conductivity. All of these are tracked inside the program so that over 60 years or 70 years, it'll change the conditions in the bioretention unit to match the real world. This is just an example of some of the equations that are used to do this process. It's very complicated, and there's a whole paper on it that we can go into, but not in this presentation. But the idea is that we're using the best equations we can to monitor this, with the idea that we're going to mimic or we're going to reproduce what actually happens in the real world. And that's what Joseph's going to talk about.
Yeah, so we got into the research regarding this bioretention facility because this facility is something in wwhm and WwH-swmm and KLIBM that you can't do this in a spreadsheet. This is a very complicated algorithm. But like I said, who cares if it doesn't match up to the real world? So in Western Washington, we actually studied this, studied its long-term effectiveness, the performance of the soil layers, infiltration, was the storage correct? And also in the software, the engineers are going to assume that these facilities will be built to specification, and we'll see if that actually happened as well. So in the second phase of the study, in the second phase we studied the bioretention performance, it was focused on matching the flow performance between the model and the observed results. And then where the bioretention facilities are built in the region of new developments and retrofits, and then really the local jurisdiction of the area, we're seeking evidence that this facility performs how it is mapped out in the model. And so they found in this study that of these 10 bioretention facilities, which were all built in the last 2 years, some of the soil was coarser than ecology's recommendations, resulting in greater infiltration. And the wwhm 2012 model, built from these field measurements of each site, adequately represented observations, verifying accuracy of the model's ability to predict performance. So it's pretty crazy that we have a model taking all these theoretical equations, applying it to an algorithm, and actually mimicking real-world performance, which in any field of engineering or any field where we're constructing something, that's actually very, very hard to do. But however, some of these facilities were not designed correctly, resulting in some suboptimal performance, and they actually found that some of these facilities were not constructed to the proper specs. So the ones that didn't perform how they should have just simply weren't built properly. And so some of the areas for the bioretention facilities that didn't perform correctly, they were smaller than they were supposed to be in the initial report. Some of the infiltration rates were higher than predicted in the model because of the coarser soil used. But they also found some other effects such as water-loving plants were a bit of a mismatch for some of these well-draining soils that we had here. And shrubs tended to survive better in the model. So what is the implication of this? Well, basically ecology is outlining, Washington State Department of Ecology is outlining some recommendations for bioretention design that it needs to actually be designed to how it's designed in the model. Because when it is designed to how it does in the model, it performs exactly like we expect it to do. So this is showing us in software such as wwhm, KLIDM, et cetera, that if we build these properly, we can use algorithms to simulate the real world. We can do this. And using in-depth equations, using continuous simulation, these more advanced methods, we can actually simulate the performance in the real world and improve our communities and our designs. So, like I said, these are just some of the bullet points and implications, but the facilities must be constructed properly on site with area and soil depths meeting the actual specifications. So you can't just wing it when it comes to the construction process. And outlined here, Ecology basically stated we needed a checklist for engineers and reviewers to make sure they actually follow this process. Because as we know, in the construction phase, sometimes corners get cut. And these facilities need to actually be designed properly in wwhm with the correct infiltration rates and areas. So they actually need to also be designed properly. So yes, there's a lot of auto-sizing functions in the software such as wwhm, but the engineers also need to understand what's going on, understand what continuous simulation is to properly design these facilities. So the answer to the question, can we trust our software designs, is absolutely we can. We can predict how these facilities will function in the real world. That's what this research is showing. And Clear Creek Solutions was able to create these bioretention algorithms basically from scratch, and then we're able to perfect them over thousands of iterations that we've done. And they do actually simulate the real world circumstances that we're seeing here. So do you have any comments to add about how some of those algorithms were constructed?
Well, I mean, I can answer those questions to anyone who wants to talk about it. I just want to emphasize the fact that this is wwhm, but it's exactly the same bioretention unit that's in the KLIDM software, and it works. It represents what's going to happen when you build it. So it's really exciting.
So these are some of the works we referenced. There's actually, at that YouTube link, there's a discussion, or you can find it Clear Creek Solutions. Discussion of the study, there's about an hour discussion on it, and so that's where we got that information from, as well as a document released on it. So that's where the information came from. It was done by the Department of Ecology and combined with Clear Creek Solutions, going over just studying these facilities and make sure they performed how we mapped them out in the model, and they absolutely did. So that is our analysis there, and if you have any questions.
Anyone with questions? Thank you.
Thank you.
So, how much water? There's different ways that we model water quality. It can do full water quality modeling, where it models all of the constituents and tracks them. Most of the time, it's done prescriptive. So if you put the right bioretention media and put water through it, then it says, well, that'll do the job for these types of constituents. But if you wanted to do a full model of water quality, we can't do that. It's a lot. It's complicated, but it can be done. Yeah. Yes, it's very.
So some of Korean researchers application of HSPF
Yeah.
simulation of water quality model.
Good, yeah.
But I don't understand how to calibration.
Yeah, calibration's very difficult. It depends on how many monitoring sites you have, when they were monitored, and how reliable they are. And then when you do it, HSPF, you have an order of the things you have to model. And so some constituents you can model just that. Others you need temperature, you need dissolved oxygen, you need a whole list of parameters. We've done quite a few water quality models. they're expensive, so people don't do them that often. But we have it built into www-swmm where the user can just select a bunch of defaults and it'll pick them. And so they don't have to know as much to do the water quality, but it's still very complicated.